today, isn't it?
Yeah, but I thought it say today will be rain this afternoon.
Will it?
Yeah.
Sad.
It's maybe 12 or 30, just 1 p.m. maybe, and rain to 4 and 5. And today is the temperature, I think is 11 or 12 degrees also.
That's okay.
It's
okay.
Summer say next week will be 20 degrees.
Maybe, yeah. That'd be nice.
I can wear my t-shirt.
Yes. Yeah. Have a cold drink. Okay. Computer's so slow. Magnetic fields, you got that? Where's your notebook?
Oh, yes. Oh.
New notebook?
No. Of course not.
This is a big lesson today. Big lesson.
Yes. Easy. Today.
We'll see. We'll see.
It's the first. Just the first class.
We have a lot to do. A lot. Okay. So, a magnet. So this is a magnet. You know this word?
Yes.
Yeah. So what is a magnetic field? So a magnetic field is the area around a magnet in which there's a magnetic force. Moving electric charges can make magnetic fields. Magnetic fields can usually be seen by magnetic flux lines. The direction of the magnetic field is shown by the direction of the flux lines.
I should write the.
Yeah, in a second, don't worry, in a second. So I just want to draw here what I mean. So, here is your magnet. So this here, these are called the flux lines.
It's opposite.
Opposite. Oh, sorry. Well spotted. Thank you. These are called the flux lines. And all of this is called the magnetic field.
Yeah.
And the reason is because there's a force here. So you know if you were to bring another magnet near it, it'll push away, won't it? Yeah. So there'll be a force pushing them here. Okay. Another thing which we'll see later is if you have a charge, like say you have a proton. If that proton is moving, it will make a magnetic field around it. So if you take a proton and you just throw it, it will make a magnetic field as it's moving. And then if it stops, then there's no field. It's just as it's moving, it makes a magnetic field. Interesting. So, yeah. I think you need to write all of this.
Can you give me the third experiment name? Yes. Title.
Yeah, did I not give it to you yesterday?
You say it's in your head, but I can't.
In your head?
I can't remember I can spell the carrot.
Yeah.
It's hard. I just know the IV something.
The third one is internal resistance and EMF of a battery.
I can't remember.
It's the name of one of the lessons, isn't it?
Really? I can find it. I cannot find it.
You can't find it.
Yeah, I can.
There. There. See?
What? Is this? Is internet
Internet, internal.
internal resistance?
Yeah.
Just this.
EMF and internal resistance of a battery.
It is the first one.
No, that's the third one.
It's the, oh, I say the one.
Oh, 1 and 2.
Yeah.
Oh, that's the IV characteristics.
Yeah, I just say character.
Here. IV characteristics of a resistor.
Oh.
So we're doing IV characteristics of a resistor and a filament lamp. That's the two we're doing.
Just a resistor and a filament.
Filament lamp, yeah.
Okay.
Where is Gao?
I don't know.
You haven't talked to her?
No. I just the morning I talk to
Summer?
someone. I think it's I think just 10 minutes or 20 minutes. You will
Like yesterday.
oh. I focused like this.
Wow. Come here, Summer. Right. What happened today?
I don't know. I leave my house in 8:30.
Yeah?
Yeah, I don't know what happened.
Okay, maybe you should leave at 8:15.
No. 8:50. I missed the first class, I think.
Yeah, I have in this.
Ah, okay.
Oh, hungry.
You're hungry? Yeah. Now, what I need you to do next, this is a picture
For this.
of the field lines. Now wait, before you draw it, they sometimes ask you to draw this in the exam. Okay?
Oh, easy.
Easy, okay, fine. But the name of this one is called a bar magnet.
Oh,
This one's a bar magnet.
And then has this.
And then, yes, exactly, yeah. So, draw this one carefully. And please make sure you write the name on top. Oh, that's so small. Okay. The name, bar magnet.
Okay.
No, don't do that. Don't do that. Just write N and S.
Yes. Because I just remember bar. It's N2. Okay.
Yeah, yeah. And do you remember what these lines are called, Ben?
Flux lamp.
Flux lines, yeah. Good. Okay, you got that somewhere?
Yeah.
Okay. Now, the Earth also has a magnetic field around the Earth. And you have to be careful. I know we call this the north, but actually the north of the magnet is down here. It's like this. We call this the North Pole, even though it's the south. The reason we call it the North is because if you stand here with a magnet, because this is south, then this side will be north and this side will be south. So the north points to the North Pole, but it's really the south of the magnet. This can be confusing. Yeah, well, you know, you have a little magnet. North points up. If north points up, it must be south on the top, because north and south attract. If this was north, south, and you stand here, then your magnet will point like this. It's opposite. The north is on the bottom.
I can understand this idea. It's why I stand the north, then I keep a
Magnet? Compass. Compass, yeah.
And why I have this way is not.
Okay, let's see.
I can keep any.
Okay.
I mean, I can keep it any direction.
Yeah, but no, the compass, the moves.
Oh.
You know this? Oh, sorry, yeah, okay, yeah. Maybe you don't use these anymore. The compass, it points to the north.
Oh, I know.
You know this? So, this is wrong, because if you stand here with your little compass, then the south will stick here, because this is the north. So it must be this way.
Why?
Because you want the north to point up, so there must be south here.
But what? I think it's
Opposite.
How to call that
Compass,
thing?
compass, yeah.
The compass, the south side, contact, just contact. So we thought it's contact with Earth,
Yeah.
how to call it?
Magnetic
magnet,
field.
and the SS
Yeah.
will be moved.
Exactly, yeah. Yeah, compass. So you see, where's north? This is north?
yes.
Okay, so if that's north, then at the top must be a south pole.
Oh.
Because if that was north, and this was north, then it would be pushed that way. But if north is this way, on this magnet, north is this way, then that over there must be south.
Okay.
They must be opposite.
Yeah.
Yeah.
But why we? Oh,
Why do we call it north? I don't know. Because it's on the top. So,
actually, it's just sun.
it's yeah. So, just to be clear, geographic north equals magnetic
Sun.
south.
We don't learn the
Yeah.
geography.
You know this word?
I know.
Geography?
Yeah.
What's that mean?
You don't know geography?
I don't know.
Geography. Oh, go on. Tell them the Chinese word for geography.
D.
Huh?
D.
Oh. Oh yes.
Yes?
Oh,
Yes,
yeah.
of course. DD?
D.
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 D-I-L-I.
D-I-L-I.
L-I. Yeah.
Up, down. What's the sound?
The three. The four. The four.
Down.
Down. Yeah.
Down and
S-
up, down.
Yeah. Up down. Up
D-
down. Up down. Oh yeah.
Up,
yeah,
down,
yeah.
yeah.
Up down.
D, Lee.
Yeah. Yeah.
Okay. I'll try to remember that. Right. Now, next thing you need to draw is the Earth's magnetic field. And see, look, north magnetic. North magnetic pole. Oh, they don't quite mean. Okay, yeah.
Oh, North Polar and is
Yeah,
different.
yeah, magnetic south equals North Pole.
No, I mean it is
They're not the same place. Yeah,
I mean,
yeah. There's a little difference. Yeah. Anyways, if you can draw this, please.
oh,
Yeah.
so I can do here. Oh, it's
Beautiful, beautiful.
sorry. No. Yeah. It's south. Oh, it's north.
Perfect.
Yeah.
Good.
Just this.
That's fine, yeah. What is that?
The word.
I see. Got that? Yeah? Okay. Now, when you have a current, you can also have a magnetic field. So in this picture here, there's no current. All these compasses, this fell out.
Oh. 20, 19, oh, 18, I don't know.
Whew, close, close. Right, so in this picture here, there's no current. So all the compasses just point to the north. When you turn the current on, you see they all make a circle. Can you see that? So that means there is a magnetic field around the current. And Ben, we were talking about this earlier before you were here somewhere. We were saying that when you have a moving charge, it makes a magnetic field. Huh? Huh?
It's ampere.
Amp?
Amp.
Yeah.
Amp.
Ampoule?
No, I don't think so.
Okay.
Because I remember it's something like this.
There is a rule for this, yeah. We will do that later. Okay.
This?
Huh?
Okay, fine.
What I need you to do now is draw this. Yeah. Good job. Okay. Now,
It's current.
oh, I made this picture too big. It doesn't matter. It's actually the picture on the left that I care about. So, do you see here? This here. Sorry, Ben, do you need something from this? Now, this is interesting. If you take your current, but then wrap it up in this shape, it will make a magnetic field. The magnetic field it makes is the same as a bar magnet. This shape here, this is called a solenoid. It's very simple. All you do, you take your current and you just wrap it up like that.
Magnet.
And you make a magnet.
Yes.
Simple. They use this in like, if you had in the junkyard to pick up the car. So you have the car here, and then this comes along and goes down and then picks it up, the car, in the junkyard. Yeah, and then it moves it and drops it. The reason this is good is because you can turn the current on and off. So for example, if here's the car, you bring this over, bring it down, and turn the current on, and it pulls it up. And then when you want to drop it, you just turn the current off, and it falls. So this is a very useful magnet, because you can turn it on and off. It's called a solenoid. And again, they might ask you, and they sometimes ask you to draw this in the exam, so I need you to draw this one now. Now, make sure you have the direction. Okay, the current is coming down here. got that?
Of the name.
Solenoid. Yeah? Okay. Yeah. All right. Next. So we need to say two things that we need to be clear. So this is perhaps the rule you were talking about, Ben. This is a way to know the direction of the current, of the field. So if you have a current and the current is going up, like this, you take your hand, you put it around the current with your thumb in the direction of the current. So then this here is the direction of the magnetic field.
Do
You
we
see?
have
Yeah?
left hand rule?
Yes? Yes? Yes, you have both. Have you seen this one before?
Of course, I just say,
Yeah.
like here, I say it like this.
That's what you meant, yeah. This is called the right hand rule.
Yeah.
I don't know.
But I remember some in terms of M.
Yeah, no, that's another rule, don't worry. Could you maybe write here right hand rule? Oh, you have it, yeah, okay. Right. Next, the definition of a solenoid. A solenoid is a coil wound into a tightly packed helix. Do you know this word helix?
No.
It's the name of this shape.
Oh.
We call that
Spring.
like a spring. We call the shape.
Shape.
The shape is a helix.
Yes.
Yeah. Okay.
So, what is coil?
Coil is metal wire, like a piece of copper.
Oh. Is copper.
Some copper, like I don't have anything like it. Oh yeah, here, like this metal here. You say could be a coil
Oh.
because you can change the shape. And do you know this word, wound?
No.
Do you know this verb? It's a verb.
Word.
It's a verb, and it means to bend in a
Bend.
circle. Yeah. So it's like saying a solenoid is a metal bent into a circle helix. Yeah?
Yeah.
It's okay?
Yeah.
Ben? Continue? Okay, so far we've not talked about units. So we need to measure how strong the magnetic field is. So the way we measure that is something called the magnetic flux over a particular area of space. Is the number of magnetic field lines passing through that area. And the SI unit is called the Weber. So I'll show you with a picture. Here's my magnet. Sorry. And we call here, I would say, the magnetic flux is 2 Webers because there are 2 lines that go into it. Here I could say in this space it is 1 Weber. Here in this space I would say there are 0 Webers.
Oh.
That's all.
Wait, what?
Weber. Yeah? You confused?
So it has a Weber rule.
We'll get to rules, don't worry. Don't worry. So this is the definition of magnetic flux. Nice what?
plate,
Plate?
like some garden park.
Ah. For today?
This weekend?
This weekend? Have you gone to Dublin Zoo? The zoo? You know zoo? You know zoo.
It's not the
zoo.
the
Oh,
park.
Yeah. Have you
Where?
gone?
Where?
It's in the Phoenix Park.
Oh, in the films.
Yeah.
Okay,
It's very good.
very good.
It's very good.
Just a lot of deer.
No, other animals too. You should also go to the beach.
Oh, yeah. I know. And no.
Huh?
And
Which beach?
I don't know.
Yeah, there's some. You could go to Holt or Bray. These are easy to get to. Nice walk around, eat some chips, eat some ice cream.
Sit at home, lying on the bed.
No, that's terrible summer.
Play some games.
Ah, that's terrible. On a day like today, you should have a nice weekend.
Only half day.
You have a half day?
I mean, only.
Oh, half a sunny day.
Or maybe just chimney.
The zoo is good. The zoo is good.
Turkey? Tickets. How much?
I don't know how much it is for a student. Maybe, I don't know, maybe 12 euros? It's kind of expensive, but it's really good. It's really big. Maybe you spend like, I don't know, 2-3 hours. Okay, got that? The Weber is actually the same as volt second, but you don't need to know that. It's not very important for this course. Now, we have something called the magnetic flux density. So that is, you see this has an area, this has an area, and this has an area. So if you do this divided by this, you can get the Webers per meter squared.
Yes.
Yeah? So for example, here maybe it's 1 Weber per meter squared, because maybe there's 2 Webers and 2 meters squared. Here maybe it's also 1 Weber per meter squared. So this is called the density, and it's quite simple. It's the flux per unit area, and the formula, of course, is, now wait, the unit is 1 Weber per meter squared. We also call that a Tesla. Yes, just like the car.
T.
Yeah, T. And the formula is that.
Oh, B
Is the density.
is okay.
What do you think about the Tesla?
Expensive.
Another
Too
thing?
expensive.
Another?
Huh?
Another?
Another?
Something else?
Looks nice,
Yeah, I think it was.
but too expensive.
Yeah.
What?
The car, Tesla.
Tesla.
Well, it's a car called Tesla.
The
Electric car. Elon Musk.
I
You don't know Elon Musk?
Oh,
You know Elon Musk?
yeah, no. The CEO.
CEO of Tesla, yeah.
It's not bad.
Yes?
And electric car is very famous in China.
Yes. But China's trying to make more electric cars, aren't they?
Yeah.
Yeah.
China has their how to call their companies, Chinese companies to make
Electric cars.
yeah. But I think Tesla is the best company in
Probably for electric cars,
yeah.
but still very expensive.
But it looks very cool.
It does look very cool.
Yeah.
You have this? Yeah?
Yeah.
Okay.
The last. Okay.
Now, the B is the nearest thing we have, which is like the E for electric fields.
Oh.
So what I mean is, the bigger the B, the stronger the magnet. Yeah? Okay, so a moving charge will produce a magnetic field, and by using the right-hand rule, we can know what the field looks like. If the moving charge is in a magnetic field, then it will feel a force. We know these north repels north rules. So look, here's what I'm saying. Let's say you have a big magnet. And this is to the this is the north end, and this is the south end. Okay, and then you have a little particle like a proton. The proton moves along here. The proton will make a field, but when it gets here, these two fields will push together, and what will happen is the proton will change direction because there will be a force on it. How much force? Well, there's a formula. It's quite simple. It's QV times B. That the force will be QV times B. Now this is a special multiplication. Okay? Because the reason it's special, this V is a vector. It has a direction. This B is a vector. It has a direction. So this F has a direction. What is the direction? I'll show you how to calculate it. It's a special multiplication. I think Ben already knows it. You have to use your left hand for this one.
I don't know.
You don't know this one? Oh, okay.
What the it's not that
Now it is normal multiplication. So like for example, if Q is 1 coulomb,
yeah.
V is 1 meter per second, and B is 1 Tesla. Come on. And B is 1 Tesla, then F will equal 1 times 1 times 1, which is 1 Newton.
Oh.
But what I'm saying is that this has a direction. And what is the direction of this 1 Newton? It's a special direction. We can calculate it using cross product. I'll explain that in a moment. Right now you just need the formula. QV multiply B. Okay? But I'll explain how to do that in a moment.
So, do I need to draw the picture?
No, we'll do that in a moment.
But I don't know what is this.
I'll explain to you.
Just
Can I guess?
Go on.
Here is B, and here is B, and maybe here.
Let's see. So, how do you calculate the direction? Use something called Fleming's left-hand rule.
I don't know this. I don't know.
Okay, fine. This is the direction of the charge. This is the direction of the field. And this is the, this is the force, this is the field, this is the current. So I'll show you with an example. So say I have the field going this way, north, south. Magnetic field.
Not the sound slow. Is the same or different?
Whatever, any magnetic field, doesn't matter.
Oh, the magnetic field is the same slow.
As a solenoid? Solenoid, bar magnet, Earth's magnet, it doesn't matter.
Oh, it's the same.
Same, yeah. And here we have, let's say, a proton. A proton. And the proton goes like this. Okay. I want to know what direction is the force. So F equals QVB. But which direction is the force? Well, okay, so watch carefully. This finger is for the magnetic field. So you see the magnet goes from left to right. So this finger points right. Okay? This one is the direction of the current. The current. So see, the current is going up. So this is right, and this needs to go up. So right and up. So the force goes into the page. Goes in. So the symbol is like this. You'd say the force does this. This is the symbol for the force. That means it goes in. And if you're wondering, this symbol here means the force goes out. So what I'm saying here is the proton will move that way into the TV. Yeah?
But
yeah?
You means this?
No. This is the magnet. This is the current.
Oh.
This is the force.
Oh, like this?
Yeah.
Yes. Yes. Yeah. Easy. You get the idea?
Yeah.
This is called Fleming's left-hand rule. And if you could try to draw the left-hand rule.
Can't write Chinese.
No, of course not. Oh, wow.
What's trust? What?
Force, just force. Yeah? Got that?
It's too ugly.
Ah, goodness. Right, continue. Continue. Let's have a look at some questions. So, yeah?
Can you change? The current is this way.
This one's the current.
It's just outside.
Huh? No. Your fingers are the direction.
But the picture is
No, the current have the volt
like
the
this.
vector.
Oh, look, in the picture. Okay, look. In the picture, he only uses one finger, 1, 2, 3. But I keep my fingers together, so it's 1, 2, 3.
It likes this.
No. It's a. That
3D?
question is an example.
It's
just
3D picture.
It's a 3D picture, yeah. So, this is here, and this is here, coming to you. It's like this. 3D. Yeah.
But it's 2D picture.
I know.
through.
It doesn't matter. If you can try to remember. Yeah? Yeah? Okay. Let's have a look at a question. I think you can do this one. A bar magnet has a flux of 2 Webers. 2 Webers, the flux. So you have your bar magnet, and it has a flux of, 2 Webers.
Yeah.
Okay.
What's the
And the region is a circle of radius 1 centimeter. So there's like a circle here of 1 centimeter radius.
Radiant.
Radius.
So area.
Yeah. What is the flux density? Okay, I want you to calculate the B.
It's wait.
So what's
1
the area?
centimeter is
What's the area? How to compare that?
It's a circle.
Oh.
Circle.
pi r square.
Yes, but I don't know if Summer knows that.
Yeah, I know.
Good.
R is 0.01.
Yes.
And B equals just 2 over
Yes.
pi square is
Yes.
Beautiful.
so equals 6.28 times
2 over
no
pi.
of course it's 2 over pi.
2 over 0.000 pi, 1 pi.
Yeah.
So that is 20000 over pi.
Yeah.
How big is that, Summer?
No, it's
25465 Tesla. Yeah? Yeah?
It's 5.
Oh! Yeah, what is it?
6366.
6366 Tesla, sorry. Yeah.
It's bigger.
Yeah, I know, that would have been a problem. Okay, continue?
Yeah.
Yep. Happy with that? Okay, next one. A proton moves towards the east in the Earth's magnetic field. What is the direction of the force? Okay, so here is north, here is south, here is east, here is west. Okay, here is USA, here is China, here is Santa. You know Santa?
Santa?
You don't know Santa? You know who Santa is? He lives here. He makes the toys for the children.
Oh.
Oh, it's the
Yes, exactly. Santa, yes. He lives up here. Okay. Santa up there. Okay, so you have a proton and it travels to the east. So here you have a proton and it heads to the east. So use the left hand. What's the direction of the force?
Is it?
You tell me.
current is in
Current is right.
Or out?
What direction is the field?
Up.
out.
Yeah, because this is really north and this is really south. So it's up.
Yeah.
So
So the force.
this one is,
out.
yeah, so out. Like you said out. So the force is this way, it's out,
Yeah.
which means the proton will, imagine this is the proton and it's moving to the east. So in this picture, out means up to the sky. So the proton will go like this. It'll move up. Yeah? Yeah, that's okay? Right.
It's moved to east.
Yeah.
Here is north.
Okay, so here's north. So there's east. So the proton will move to the east and will start to move up. Yeah? Okay, good. 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 Okay. An electron enters a magnetic field and then experiences a force. The flux density is 250 millitesla. The electron is moving at 1/10 the speed of light. What is the acceleration? Okay, so in this one here, we need to use
QVB.
QVB. Okay. Right, see if you can calculate this force, this acceleration.
Easy.
Good, calculate. You can use Summers' calculator.
What's the B? Oh, what's the V?
The V says there, 1/10 the speed of light.
5-1.
Mm-hmm.
I
Good.
Is the light speed is 314 meters.
It's about 3 multiplied 10 power 8.
Well, how about
That is the sound speed. So
Yeah.
what is MOT?
What's what?
MOT.
Huh?
maybe Tesla.
What's what?
MOT.
Yeah.
M?
215 MT.
Millitesla.
Milli.
Milli. You know milli.
It's
Like millimeter.
Sir? Minus sir.
Minus 3.
Minus.
You know this. I do.
What's the speed of the light?
3
Yeah.
multiply 10 power 8.
10 power 8.
Yes.
Oh, fast.
What is Q?
It's an electron.
Oh, just one. QO.
It's 1.66.
Times 10 to the minus 19. Or something.
18.
I don't remember.
19.
QVB.
Yeah.
V is the line.
1/10.
But why you say the line?
Huh?
The sunlight.
No! Ben, the electron is moving very fast. I'm saying the speed is the same as 1/10 the speed of light. Because it's so fast. Ooh, seems very big.
Yeah.
That's the force. I want the acceleration.
Oh.
Are you sure?
Let's have a-
Let me see.
I think.
It's
Oh,
Minus
minus
19.
19.
Come on.
Sorry.
it's this one.
That looks good.
Sorry.
So, here. Look,
Just multiply. Just over
over M.
and
So look, F equals QVB, but F equals MA, so you can say MA equals QVB. So A equals QVB over M, which is E times 1 over 10 times C times 1 over 4 over mass of electron.
proton. It's
Electron.
Oh, yeah, electron. It's 9.11 times 10 1.32 times 18. 18.
18.
18.
80?
18.
1 8.
Yeah,
Yeah, 18.
18.
What's the math?
I gave it to you in the previous lesson. Now that's easy kind of, but now I give you a hard part, okay? So let's draw the picture. Let's say north, south.
The question in your head.
Here, huh? No, I don't like that. North, south. There we go. And then here's the electron, and it's moving this way. So what's the force? Okay. This is down, and what's the current direction? Left or right?
It's right.
It's left,
Uh,
because it's an electron.
Current is here.
Left.
Here.
whoa.
Force is out.
Yeah.
Current is left. Not right.
Current is
Why
right.
current is line?
It's electron.
Yeah.
Remember in electricity? If the electron moves from A to B, we say the current is from B to A.
So the V is
To the right.
V.
Yeah, this is V.
To the right.
Yeah. The current is to the left.
So it's
Out. So it's like this. It's out. Yes.
The V.
No, left. That's not V, that's current.
this current.
Yeah.
3 is current.
Yes.
And this is
It's field.
field.
Yeah. So anyways, look. This is going to come out. So what will happen if I try and draw this like in a box? And like this was north and this is south. Okay? Terrible, I know. So what happens is the electron comes in, and then when it enters here, it will curve like this.
Oh, nice.
Because you're standing here, looking at it.
3D.
3D, yeah. So what will happen is, it will move in a circle. It's moving in a circle. My question now, calculate this.
Where is the file?
Not important.
Oh, my.
Not important. I give you a hint. You need to use this answer. This will help you.
The same? Oh.
Yeah, same problem. It's an electron. Calculate or. My hint is remember circular motion formulas in mechanics.
Can I say the I have the answer.
The V is constant.
Same V.
So it's V squared over R.
Very good, Ben.
A equals, and you know V, you know A.
Yeah. Easy. Ben figured it out. You have to use the formula from circular motion. A equals V squared over R. Yeah. So R equals V squared over A, which is 3 times 10 to the 7 over 1.32 times 10 to the 18.
It's 18?
That's what you said, isn't it?
Oh.
Isn't it? This right?
Yeah.
So it'll be small.
1.36.
Square. Way square.
Oh, sorry. Thank you, Ben. But still small.
Yeah.
What is it?
Let me check.
What?
7 square. 1.32.
0.00681. I think it's
Minus
681.
Repeats. Centi. Okay, 10 to the minus 4, isn't it?
Yeah.
So it's 681 micrometers. Yeah.
Oh
Six-
yes. Yes.
Now look, in the exam, what they sometimes do is they put this formula and this formula together. So you can say QVB over M equals V squared over R. So R equals MV squared over QVB. But of course the V's cancel. So you get R equals MV over QB. That'll give you the same answer. This is in the formula book.
If I should draw the box.
No, otherwise you want to. What's wrong?
It's gone.
You did so much physics, it's gone.
I love this
I know, much more than EAP.
class.
Did you have the English class this morning?
Yeah, this one the new.
How is it?
Just talk about critical thinking
Okay.
and how to do the link.
Links. Okay. Good. How
It's
many students in the class?
1, 2, 3, 4, 5.
Okay, that's okay. And what teacher?
New.
Neil's okay.
Um,
Is Neil friendly teacher or angry teacher?
friend.
Okay.
I think he's a middle teacher.
Middle, okay. Well, it's different for you.
Yeah.
Different for you.
I know.
You make him angry.
Yeah. But I still thought he's a middle teacher.
Okay,
Yeah.
okay.
Okay.
Yeah.
No.
So if you want, you can just use this formula. You know. If you just use this formula, you get the same answer.
Yeah.
That's fine in the exam. You can do that.
So in the final exam, we will get a
A
physics formula
Yeah,
book.
yeah.
It's different from in the mid test. We just have one page.
It's the same as the end of semester 1 test. Do you remember? At the start of the exam, you had all the formulas.
Yeah,
Yeah.
but it's just one page.
No, it was more than 1 page.
Yes.
It was like 4 or 5 pages.
Actually, I think any unit, your idea.
The idea is most important. Yeah.
How to combine this and this.
Yeah.
But
Yeah.
I
True.
think
That is very true. Very true. Hey, Mark.
You here?
I believe we
You
are.
look like you're here anyway.
Yeah, well, we're doing our physics. Are you in here next or?
Maybe we're down below, but the students thought we were up here. We have a funny timetable thing going on Friday, so
I'm in B401 pretty much all day today.
Grand. Okay, leave it there, so.
Grand. Yep. Now, what was I saying? Oh yes, on the exam, the first page is the title, and then it's like 2, 3, 4, 5. It's the formula book.
Useful formula. Since they won't give us the useful.
Ah.
All the useful formulas. I think.
They give you some useful formulas. Like to give you this
Just
one.
Just a song.
What do you want? Want everything?
Everything.
Okay. Is this one okay?
Yes.
Okay. So this is kind of a big lesson today. I think we'll just do. Maybe we'll just do this one. Let's see. How many questions do you have there?
5.
Oh, before you start, actually, I want to talk about your chemistry. Yeah, in chemistry. Wait. Chemistry. You did mass spectrometer? Hey, I think you guys are downstairs. Are you business? Business students, come back.
No.
Business. Oh, Mark.
Yeah.
We have some business students loitering around.
I know, I'll take them. I'm waiting for the rest of the students.
Ah,
to
okay,
come
fine.
later. I think we'll have a lot of business students
Grant, okay.
loitering around.
It's under control.
It's what do we call this type of control? It's a flock of birds control.
Okay. I was teaching the students the word, and you nicely demonstrated it for us, the word grand. It's a very useful word. You can use it in lots of situations.
In Ireland.
In Ireland. Yes. Yeah. So that's grand.
Grand.
Right. So you in chemistry you did mass spectrometer, didn't you?
What?
Mass spectrometer?
Can you talk details? I don't know what I do. You know my English.
Okay. You have a particle, you fire, and the particle spreads, and you can calculate
You
the
mean this?
like this picture, yeah.
Oh, I know.
You know this in chemistry, yeah. So what happens is you have 2 parts. So first you have electric field
Electric field. And magnetic field.
and a magnetic field, correct, yeah. So you have your whatever it is, whatever material it is. Yeah, whatever it is, your sample, okay? And the sample has a charge, and it enters the electric field.
Oh, it's positive.
That doesn't matter. Yeah, it's positive. You use the electron gun,
Yeah, shooting.
shoot electrons at it. Yeah. So this has a charge. It enters the electric field, and you know the formula Q V equals a half mv squared. So it'll come out here going very fast, and then it enters a magnetic field, and it will move in a circle.
Yeah.
And you have the formula F equals QVB, and this V is the same as this V.
Oh.
Okay. But you can use the formula or equals, what do we say? MV over QB. MV over QB?
Yeah, QB. Small Q.
Well, just get
Small Q.
okay. So what you can do, you can change this into M over Q equals or B over V. So you can calculate V easily using this formula. You can know B because it's on the magnet, and you can measure or. You can measure.
Yeah.
So if you calculate this, you can know this, which is the mass to charge ratio
Oh, yes.
in chemistry.
Yeah.
Yeah. So this is how you can do this using physics, electric field, and magnetic field together. You can calculate the mass to charge ratio. Yeah, I think it's interesting. Yeah, that's what the last question's about. So you see, first you give it a charge, then it enters. What's this one? What's this say?
Source of electrons to burn.
Oh, this is where you give it a charge. Yeah, so first you heat it, make it a gas.
Yeah,
Then you fire electrons on it, shoot electrons, give it a charge. Then it enters an electric field, accelerates. Then it has a V. It enters the magnetic field and it curves.
Yeah.
And the radius depends on charge and mass. So you can use a computer here, calculate the radius, and gives you the information. It's very interesting.
It's physics.
Physics meets chemistry.
But I think
More physics.
more physics.
Agreed. Okay, so we got a few minutes left. I think this is good. You can do these questions now. Yeah, like 15 minutes. You can get this finished in 15 minutes, right?
Try.
I think you can. You're both very smart,
No.
but Summer's using his phone.
What
Not
happened?
smart.
What happened? I want you to do these.
You are smart.
No, man. No. My English is just good.
No. Language is a part of smart.
Is it?
Yeah.
Yeah.
I think so.
Maybe.
But that's your
First language. Yeah. Yeah, my Chinese isn't so good.
so do you learn
You
other
don't know
language?
how long
Irish.
time we studied English. we began to study English in the primary school.
Yeah.
So long time.
Chinese English is difficult in school.
It's very
I
difficult.
understand. Do you think Gal will watch this video later?
Yeah, I think
She will?
She will.
Yeah.
Should we leave a message for her? We could say something and we'd see if she watches it. So, if you're watching this, then for the next class, I would like a cappuccino and a pastry for me. I'll share it with these two people. Yeah? Now we'll see if she watches. So if she comes to class with a cappuccino, she watched it. No cappuccino, she didn't watch it. Right?
Maybe he will.
Huh?
He will
Dislike?
She
Oh,
will-
also, yeah, like my video. Thank you.